the input, and the y-axis is the running time in terms of the steps, right? So as you can see that at 20, when the size of the input is 20, the red curve, which represents the 6 squared term, is contributing more to the growth of the overall function. And the 100 plus 300, as we increase the size of the input, is almost kind of linear, right? I mean, it doesn't grow much. So if you think about this chart, it means that if you increase the size of the input, and when I say size of the input, imagine it is the size of the array to 1 billion or trillion, then this particular line, the green one, the blue one, sorry, which represents the 100 plus 300 terms, are called lower order terms that do not contribute much to the overall growth of the function. So we are going to ignore this, and even we will ignore these 6, because when n becomes extremely large, the contribution of the 6 doesn't matter anymore, and the most dominant term is n square. So we are going to say that the running time of this particular algorithm, which we derive as 6n square plus 100 plus 300, is going to be n square, the most dominant term, the term which contributes more to the overall growth of the function. And in this particular second chart, I've reduced the amount or the coefficient of the n square by a factor of 10, and I have increased the other two terms. If you observe on the previous slide, it was 100n plus 300, but now it is 1000n plus 1000. So I have increased these two terms by a factor of 10. And as you can see, again, when the value of n is somewhere between 1000 and 2000, the red line representing the 0.6 n square is clearly dominating the other two terms. And if we increase the n more and more, this difference is going to be increased as well. So long story short, it means that whenever we derive an equation or a function from a code, we then have to think that which is the leading high order term, the term which contributes more to the growth of the overall function. And we have to only concentrate on the main part and throw away other details which does not matter when the size of the n becomes extremely large. So now let's talk about asymptotic notation. We would say that the running time of this algorithm grows as n squared, as I mentioned before, dropping the coefficient 6 from the 6n squared term, and the remaining terms, which are called lower order terms, because their contribution is nothing as compared to the n squared term. When n becomes extremely large, this is an important thing to remember, because when I say n means the size of the input. And for you to understand it clearly, you imagine the size is the size of the array. So if the size of the array is 1 trillion, for example, these two terms, 100n plus 300, they are almost negligible. And even the coefficient 6 doesn't matter, because it's a constant, it remains constant. We have to focus on the n square term, because when you square something, it's going to double every time. So by dropping the less significant term, which in this case is going to be 100n plus 300, and constant coefficients, which was 6 before it was 6n squared, so we drop the 6 as well, we can focus on the important part of the algorithm's running time, its rate of growth, as I mentioned before. So when we drop the constant coefficients and less significant terms, we are left with something called asymptotic notation. So we say that f of x simply means this particular function, 6n squared plus 100 plus 300, is asymptotically equals to g of x, which is mean n square, right? So we represent n square as a function g of x, and it should be g of n, by the way. X means it's a variable, but we are talking about the size, so it's not n, it's not x, it's going to be n, right? And it's going to be n as well. So this is a mistake on my part, sorry for that. So there are three forms of asymptotic notations: the big theta notation, which is represented with this Greek theta symbol, and the big O notation and the big omega notation. Let's talk about each of them one by one. So what is the big O notation, right? It's an asymptotic notation for the worst case or ceiling growth for a given function. So it simply means what is the worst time, what is the maximum time this algorithm is going to take on a size of input, right? So it guarantees that this particular algorithm will not take more than this. So we actually defines an upper bound for an algorithm's running time, that this algorithm will maximum take this much time but not more than that. It provides us with the asymptotic upper bound, as I mentioned, for the growth rate of the runtime of the algorithm. So f of n, this is the actual function 6n squared plus 100n plus 300, which I mentioned on the previous slide, is big O of g of n, which is another function, if for some real constant c, which is greater than 0, and n naught. N naught is some value of the size for which the actual function is always be lower than the upper bound. So f of n is less than or equal to c times g of n for every input on size n, where n is greater than or equal to n naught. So let me just go back to the slide and explain what it means. So here the n naught is going to be 20, because at n naught and the values right to the n naught, I mean greater than n naught, this particular curve, the red one, is dominating the curve of the other two terms, and that means we are going to ignore them for very large values of n, right? So n naught means there is some value of the input, right, when n is equal to that or greater than that, right? The size, when the size is 20, for example, 20 represents n naught, or greater than 20, the other curve, which is the red representing 6n square term, is going to dominate, and this is actually the term which contributes more to the growth of the overall function. So let me give you an example of the big O. So let's talk about this slide. See, this is the actual function, the red one. It was taking more time for some, and this is representing the size values of n. Let's say the size was 100 of the array, then 200, then 300, and suppose there is this size which is 400, and at 400 we observe that the actual function, the running time of some algorithm, will always be lower than the upper bound. So actually we defined an upper limit, the maximum time a particular algorithm can take, and this is called the worst case analysis. And for such particular by the way, this is big O, not theta. This is big O, not theta. Sorry. So for most of the algorithms, we are going to be concerned with the upper bound, and we're going to say, okay, this is the algorithm, and we guarantee that no matter whatever is the value of the input, it's going to always take a time less than this, not more than that, right? So this is an important thing to remember. Now let's talk about the big omega notation. It is about the best case analysis, that minimum how long does it take. It's not very important because it really depends on the for example, if we talk about arrays, it really depends on how nearly the elements of the array are already sorted. For example, if we are applying a sorting algorithm, so we are always concerned with the big O notation, which means we want to talk about the function is that how maximum time is going to take to sort these elements. But anyways, I'm going to talk about it for the sake of completion. So big O notation is used for best case analysis or a floor growth rate for a given function. It provides us with a asymptotic lower bound. That means the particular given function for some code, let's say for some sorting algorithm, is not going to take less than this time, right? The big O was for maximum time, and the big omega is for minimum time. So we say big f of n, which is the actual function, is omega of g of n if for some real constant c, which is greater than 0, and n naught, which is equal to also greater than 0. F of n is actually greater than, right, or equal to c of g of n. It means it's not gonna be lower than that for every input size n when n is equal to or greater than n naught. So let's talk about that. So this is the actual running time of the function, and we define a lower bound for this function, which we called theta of g of n, that this particular function, which represents some algorithm, steps of the algorithm, is not going to take less time than that, right? Not less time than that. This is the minimum time it can take, the above function.